Hi, hello. Welcome to section number 9. Next to last section, only one more section left. Okay, QR code for today. Our question is, what's your coffee, tea, boba order? I'm a classic, simple, like hot latte, cappuccino, even in the summer. Hot drink. It was really lovely touching base with you all. I think I met with all but like 5 students in the class, and so it was really nice to have a chance to just like check in and see how things are going. So our game plan for today, basically we're going to spend the first hour or so on content from lecture 9. We're going to start off with radicals, which was really introduced in lecture 8. But I'm glad Logan brought it back at the top of lecture 9, and we're going to talk about it now. Then we're going to talk about EAS reactions and spend a little extra time on Friedel-Crafts reactions. You might notice that there is a blank lined column, and it's because I haven't liked how I've taught it the past several years, so I've tried to plan out a new way of doing it, but didn't have time to typeset it. So it's going to be a little hodgepodge, but I'm going to try to hit the main things that are important that I think that you should know. Then after that, we're going to talk about directing effects, which is going to be a big part of the theory kind of questions for the exam. And that's going to be most of the topics. Aromaticity got bumped to a video. So aromaticity is kind of a more discrete one-off skill, and so I have a QR code in here that will take you to a little video where I walk through my kind of spiel on aromaticity, the little electron hamster wheel. Yeah, wow, I feel so much more stable. But, so that is there on the content side. And then for the last 30 minutes of sections, we're going to do How to Study Reactions Part 3, not the remix, the 3-mix maybe? And we're going to talk about a few more study strategies. And finally, we're going to do one more hard synthesis together from the extra challenge problems, which is probably the hardest synthesis that we have given y'all to this date. And so I think it would be really good to work one of those hard ones with y'all. So again, game plans, first hour kind of content stuff, last 30 minutes, how to study reactions and synthesis. Any game plan questions, logistic questions before we jump in? Yeah.
I have a question about synthesis on the exam.
Sure.
Like we did in the last one, is it usually going to say how many steps?
Yep. I will always say how many steps. And I think that y'all's will be between 7 and 12, somewhere in there. The ones that are likely to be longer are the DCC synthesis, because there's so many protection steps already built in. That's 6 steps alone. Yeah. Other logistical questions? Okay. Let's try it out. Radicals! They're a time. The radical stability trend follows the exact same trend as the carbocation stability trend because radicals are a deficiency of electrons just like a carbocation is. It's a half-filled orbital. So we see our secondary and tertiary carbocations, second and tertiary radicals are the ones that are most stable. And then beyond that, we can stabilize a radical via resonance. Our resonance arrows for this just look a little bit weird since we have those single Fish-Hook arrows. So what you would do here is you would have one electron from that pi bond come in and the radical come in. The other electron from the pi bond goes to the other side. And that would produce the radical where our double bond's over here and our radical is on the left. So we can stabilize it by resonance or we can stabilize it by hyperconjugation. And our main kind of core reaction that we have within the radical family is radical bromination. So in radical bromination, we do our alkene with HBr, which normally alkene HBr, it would make our Markovnikov addition of bromine. But if we add in peroxides, ROOR, ROR, and we do it under heat, or HV means UV conditions, then what we'll find is our product is actually not the Markovnikov. We get the anti-Markovnikov product. I have a little FYI box here, both on the reagents of the delta and the HV, and then also what are some common examples of this ROR. This is, again, just kind of FYI. Nothing on this is going to be tested beyond just what's the line reaction here. But generally what we're going to see with the radical reactions is this is our base reaction, and then we can do kind of weirder things. So we want to make sure that we have the simplest base reaction down before we do weirder things.
What does delta or HV mean?
Delta means heat, HV means UV light. So we need something that's going to kind of like energize the molecule to spontaneously break into radicals. Yeah. The big thing with this kind of peroxides here is whenever you have a sigma bond between two electronegative elements like OO or NBr, or I think there's like an ON maybe on the P set, these sigma bonds are actually unusually weak and they like to homolyze. So they like to fall apart where each partner gets one electron from the sigma bond. And that will make our radical initiator. But we will see that over here. So, jumping into the general mechanism, all radical mechanisms have three phases to them, beginning, middle, end. So we start off with initiation. This is how do we generate our reactive radical buoy. So we start out with our radical initiator here, our peroxides, and this bond is going to homolytically split. So it's going to split evenly where each one gets one electron. We get two RO dots out of that. Then RO dot's going to interact with our HBr. It's going to split this bond so that the OR dot grabs the H, and then we get a BR dot. And this is going to be our main reactive radical that will interface with the molecule. So these initiation steps are basically the same for every radical mechanism, and they are like free points. So like, if you can do this in your sleep backwards, upside down, while restrained, then you get at least 3 points on the test, easy. Then the propagation is kind of where things get messy, where shit hits the fan. We have our alkene, and what's going to happen is we are going to break our pi bond. One electron from the pi bond is going to join Br dot, and the other one is going to go onto another carbon. Now, when we do this, we are always going to be trying to make the more stable radical. Hypothetically, we could put the radical on this side and the bromine on this side, but this radical is not as stable. This is a primary radical versus this is a secondary radical, and we're always going to form the more stable radical when faced with a choice. So again, we're making a more stable radical, and then from here, what we are going to do is we're going to take a hydrogen from another equivalent of HBr. So just like RO dot interacted with HBr, grabbed an H, made a Br dot, our intermediate here is going to react with HBr. And with that, we make our product. We've added the Br, we've added the H. It's been anti-Markovnikov. And the big thing is, we make another Br dot. She has done her job, and then she's kept it pushing. She's going to like pay it forward. So propagation, we started with a radical, we end with a radical. Initiation, we started with no radicals, we ended with a radical. Like we started getting messy, we stayed messy. And then termination is, okay, let's stop being messy, let's clean this up. So with this, why do we do anti-Markovnikov? Why does this happen? It's because when we do this with HBr, the step that we are doing first with normal HBr, no radicals, is we're grabbing the hydrogen first and making a carbocation. So when we grab the hydrogen first, make the carbocation, again, our guiding principle is we want to make our most stable carbocation here, and our H is added to the less substituted side. Here, we still want to make the most stable radical, but the thing that we are adding first is a bromine, and that's why the bromine gets added to the less substituted side. In both cases, we are trying to make our most stable radical or carbocation, but it's just different the thing that we add first, if we are in radical conditions or not. Okay, so termination, the last stage. This is the boring part. We rarely ever ask you to draw any termination steps because we got our product up here. So, and also like there are lots of just different ways that termination can happen. We have never asked you to draw termination steps, but it's basically how do we go from having radicals to no radicals? Well, we had Br dots. Two Br dots could bump into each other, make Br2. Or, like, very minor product, you could have this intermediate with a radical bump into another Br dot, in which case we get this side product.
Do we have to state the side product?
No, we never do termination, really. Yeah. We only care about how do you make the product that we ask you to make. So because there's so many like ways that we terminate a bunch of side products, it's just not really worth thinking about. So we can kind of ignore her. She will be easy points in the exam. She will be messier and harder. Before we talk about kind of more complicated things, are there questions on this base reaction here, this like core Platonic ideal of radical bromination? The single fishhook arrows feel a little bit weird and just takes a little time to get into. Okay, so this is a standard reaction, but like carbocations, radicals can do funky things. And namely, two big things that they can do is they can open a ring or they can form a ring. And that's going to make transformations that look really weird and intimidating. So what we need is we need a game plan for, hey, we have this core mechanism in our head. We're going to have crazy transformations on the paper. How do we organize ourselves? And the gold standard strategy is number your carbons first. Number all of your carbons even if you don't think you need to. Then make a list of every bond that needs to be made and broken. So we are going to do this. When you are doing this, watch out for hidden hydrogens. Because you know our reaction, we said we added an H and Br, but if we draw our little skeletal structure, that H is implied. And so in a weird transformation, you might not know which carbon is getting that H. Then the last thing is observe radical mechanism norms. Generally speaking, if you have the option to form a more stable or less stable radical, you'll form the more stable one. You're not going to have more than one radical on a molecule at a time. Most radical propagation steps have 3 arrows at a time, 2 that make a bond, 1 that makes a new radical. But with that, let's do this analysis and do this first one together. Simple radical mechanism. This is page 18 of the Scale Builders. So I'm going to start off, and I'm going to number my carbons up here and starting materials. 1, 2, 3, 4, 5, 6, 7. Then it's kind of hard initially to figure out where we are mapping this onto the product, right? Because it's kind of busted open. I can guess that either this is 1 or this is 7 probably. But the other thing that can help you with the anchoring is typically the first step is going to be your alkene getting a Br dot added. So given that, if our alkene's going to get a Br dot added to its less substituted side, I'm thinking that 1 over here is over here. Do you buy that argument? Cool. So then I'm going to keep going 2, 3, 4, 5, 6, 7. And that to me seems the more apparent. You could do 3, 4, 5, 6, and then 7 as a methyl off of it or something. But it seems much more likely if we're going to form a straight chain, let me find a straight path for my labeling. So now, y'all are going to help me out, and we are going to make a list of bonds to make and bonds to break. So someone give me a bond that we made or broke. Yeah, so we are going to be a little bit more specific and make it all with numbers here. So we want to make a 1-bromine bond. Great. What else? Yeah.
2, 3 alkene.
Yeah, we're making a pi 2, 3. Yeah.
Hydrogen on 2.
So
Oh, 2, 1.
hydrogen on 1. 1 had 2 hydrogens here. Has 2 hydrogens here. Hydrogen's the hardest one to spot. Let's do more obvious.
Right, 3, 6.
Yeah, so we broke 3, 6. That's going to make this come open. And then we also broke the pi bond here, so pi 1, 2. So now we have to figure out where the hydrogen is, right? So there are a few ways that you can think about it. You can literally go by one and say 2 has 1 hydrogen, 1 hydrogen, 1 hydrogen, 1 hydrogen, 2 hydrogens, 2 hydrogen. You check all of them. But the other thing is, where do we break a bond? Between 3 and 6. 3 has 1 hydrogen, 6 has 1 hydrogen here. 3 has 1 hydrogen, 6 has 2 hydrogens. That's our hidden hydrogen. So we need to make a 6 hydrogen bond. And again, I'm not being super specific with like sigma 1 bromine or whatever, mostly just because this is a tool for you. So now that we are here, we start off by doing the initiation. And the initiation is the same every single time. So we are going to do it really rapidly. ROOR is going to homolize, and we're going to make 2 RO dots. RO dot is going to interact with HBr. Boop, boop, boop. And that makes ROH and Br dot. Now we're ready to actually start the propagation. You don't have to write initiation, propagation. I think it's helpful just mentally to kind of like divide it up. So now, we already said that the first step of propagation is pretty much always the same, of our alkene's going to interact with our Br dot. So boop, boop, boop. I don't know why radicals are boops to me, but it's like very like boop. Okay, so when we do this, we are adding our bromine to the less substituted, or more substituted side. Wait. We're adding our radical to the more substituted side, bromine to the less substituted side. And already, what goals have we checked off in terms of our make and break? We made our bromine. We broke our pi 1, 2. Cool. So everything else that we have to do is related to this list, right? This is every bond that's made and broken. So right now, my radical is on carbon 2. Which goal do you think I might want to do next? Yeah, right? Like 2 is where our reactive site is right now. We want to make a pi bond between 2 and 3. We need to get an electron from somewhere else.
Do you have any formal charges on
Nope. So yeah, you can double check, but here carbon has a valence of 4, minus 3 bonds, minus 1 lone pair electron. I know, it's weird. It feels wrong. Okay, so we want to make a double bond here between 2 and 3, right? And we need another electron from somewhere. So if we need an electron from somewhere, we have to break a bond as well. Because remember, we're doing 3 arrows at a time. So that to me is suggesting we need to do these 2 steps next. We need to break the 3,6 bond and use one of the electrons to make a pi 2,3 bond. So let's do that. I'm going to split this. One electron's going to go towards a pi bond along with 2, so radical. So those are going to come in, form a pi bond. And the other electron in the 3,6 bond is going to go on 6. So now, at this point, we've done all of our goals except for adding the H on 6. So I'm going to bring in my HBr. Boop. And I'm going to finish it out, getting our product, and generate another Br dot. So that is the core strategy every time. You are numbering carbons, mapping them onto each other, making a complete list of bonds made and broken, starting your standard reaction, and then using your list to inform where you look next.
It might be a stupid question, but could you use ROH instead of HBr for the last step?
No.
Where you,
I mean,
Can we form like?
yeah, I see where you're saying. It's because HBr is much more acidic. It's likely going to be the one to break first. Yeah. And also, like, think about this: the ROH is going to be made generally a much smaller yield than HBr, which is one of your solvents. Yeah. So this is kind of a simple example of a radical question. Let's look at a harder one, and we're going to still do it together, okay? So she looks kind of crazy. She's challenge problem 7. We had a triangle boy. We had 2 pentagon boys. Then, at the end of the day, somehow we have a carbonyl. We don't have a triangle boy. We have a hexagon. Still a pentagon boy. But gross, right? So, okay, let's start mapping. I mean, this junk looks the same. Actually, this whole 5-membered ring looks the same, right? So I'm going to start numbering at the nitrogen, or like right above the nitrogen here. So 1, 2, 3, 4, 5. And I think that that's good for my carbons. Now, if we think all this is the same, the nitrogen is the same girl, right? I feel pretty confident that this is still 1 up here. Okay, 1, 2. Could this still be 3? Well, 3 here in the product has a double bond to O. And here, 3 is connected to an O, right? Okay, ostensibly, I think that that should work. And then between the other 2 carbons is 4 to 5. Well, I guess it seems logical. 3 is connected to both of them over here. And 4 and 5 are totally symmetric, right? So it kind of doesn't matter which way we number it. I'm going to just do 4, 5 like this. So, given this numbering, y'all are going to make my make and break list. Somebody, anybody, give me a bond, any bond, made, broken. What?
The pi bond.
Pi 3O, I guess. Louder. 3, 5 was broken, yeah. 5 N was made.
Bond was broken?
Yeah. And then we don't have anything else, right? We don't have an HBr actually. So I don't think that we even added an H. But also if we don't have peroxides, what's our bond that's going to homolyze, that's going to kick this process off? Which kind of bonds did we say like to split equally? Bonds that are kind of like RO-OR. What do you notice about these? They're both electronegative. Sigma bonds between 2 electronegative elements. Where do we have that over here? Exactly. So our first step is we are going to homolyze the NO bond. Okay.
Will it be obvious like this when we should do this type of?
I mean, if this feels obvious to you, then yes. Like, it's not going to be more, like, buried than this.
Okay.
Yeah. But, like, this is one where we want you to be able to look at the molecule, see the ON, and be like, yeah, that can homolyze.
ROR is like pretty obvious when they use that as like a.
Yeah, ROOR. And also HV and delta are your hints. We're never going to use those really for any other reaction for this class. And actually, to be so honest, I'm not going to draw the rest. You will on your problem set. But I'm going to call this R, and I'm going to call this R. And I'm just not going to draw it. because I make the rules here. So we broke the NO bond. Okay, so now, where do you think we're going to go next? We can either do N stuff or we can do O stuff, right? Well, we could do N and 5 together. But right now, if I like bring in my numbers, 1, 2, 3, 4, 5. Right now, 5 is not super reactive and it's not really close to a radical, right? So like, if we broke this 3-5 bond here and like one of them went to nitrogen, one went over here, we'd still have 2 radicals, which is not our favorite. Hypothetically, we could do it. I'm more inclined to try to do something with the O radical, because we need to bust open this ring in order to make 5 a little bit more reactive. So let's try to make our 3O pi bond. And then we need an electron to come from somewhere, right? So where should the other electron come from to make our 3O pi bond? From the 3-5 bond, right? So 3-5 bond, 1 electron goes in here and it meets the 1 electron from the O. And then we're going to push off the other electron in the 3-5 bond onto 5. So now, this one isn't great, right? This is a primary radical. But we can indeed form primary radicals in a radical mechanism, particularly in a propagation. And it's because the hard part in a radical mechanism is getting started. It's generating your first radical. But once you have a radical, then it's kind of like we're partying. Anything could happen. I don't know. Primary radicals? Sure, maybe. So with this, we have made our 3O pi. We've broken our 3-5. Our only other thing that we can do is make 5N. Boop. Boop. So this challenge problem, hard radical question, had 3 steps. I think the hardest part about this is visually seeing what's going on and then doing your analysis. From what I have found, students who do not do a make and break bond don't get half of the points. Like, I don't know how students do it kind of without this, but you need a structured way of thinking. And there are some students who do, but they are numbering it in their head and just keeping it on their head, which that's great for you if you can do that. I need to make and break list. So, you got a challenge problem done. Radicals, are they feeling a little bit better? You are guaranteed to have 1 radical mechanism question either on exam 2 or on the final. It's kind of like you're guaranteed to have 1 DCC synthesis either on exam 2 or the final. So that means if it does show up next Thursday, it will not be on the final. And if it doesn't show up on Thursday, it will be on the final. Yeah.
I feel like I think Logan said yesterday too, with like, if you know what the product is, don't question the steps. Like, don't be like, why is this happening? Like,
Yeah.
it has to happen. But I do feel like it's confusing that we would make like a 1' radical, or like, I don't know. I just feel like there's a lot of steps in some of these that we've been told not to do.
Yeah, I mean, so there are kind of 2 sides of it. One side to be like, okay, if we do want to think through the why of it, think about the fact that we had a 3-membered ring, which had a lot of angle strain, and then we had a 5-membered ring, which had a little bit of angle strain, and at the end of the day, we have a 6-membered ring, very little strain. So there is kind of like a thermodynamic reason of our product is more stable, and so we are willing to go to high energy intermediates to overall become more stable. Moreover than that, we made a pretty high delta H bond of our carbonyl, CO double bond, and before we had this more reactive ON sigma bond. So we can think through it a little bit, but honestly, I don't think that is as fruitful as we are wanting you to explain something that has happened. Like, most of these questions we are pulling from literature, and this just happened. can you explain how it happened? We are wanting you to that's the skill here. And so would be next to impossible for us to give you a question like this and be like, what happens? Oh, like that. There are too many options for what could happen, and figuring out what nature chose, But yeah, I feel you on that tension. Cool. Oh, I should have played my next transition, I guess. I should have played it before doing this harder radical, but the stranger radical rearrangement. Okay, we'll move on. EAS reactions, electrophilic aromatic substitution. This was our main reaction family for lecture yesterday. And the purpose of EAS reactions is to add stuff to benzene. Now, in a reaction, we need nucleophiles and electrophiles, right? Benzene has a lot of electrons because it has resonance, but it's not very reactive because she's super, super stable. She's aromatic, right? So benzene is a nucleophile, but it's a crappy nucleophile. What we have to do in all of these reactions is we have to make not just good, but excellent electrophiles so that a benzene will go and attack it. Because, again, it's a really bad nucleophile. It's really stable. It doesn't want to break its aromaticity to go and attack something. So these really great electrophiles that we make, they are so reactive that they are not shelf stable. We have to make them in the middle of a reaction, which is in situ. We have to kind of put them all together. Our general EAS mechanism is actually pretty easy. It's 2 steps. Our benzene goes and attacks a really great electrophile. When that happens, it robs this carbon of a bond, so it has a carbocation in the ring. And here we have an electrophile and the hydrogen that was originally there added for a brief moment. Then what we are going to do is we are going to restore aromaticity by removing a hydrogen. This is kind of like an E1-like step where we have a carbocation and we're doing elimination. And then we reform aromaticity. So kind of our 2 steps are we attack the electrophile, we restore aromaticity. That's the general plan. So with this being kind of the easy mechanism, the harder things are going to be directing effects in theory, which we're going to talk about. And then also the more idiosyncratic steps are how do we form our really good electrophiles. So for this, our EAS line reactions are kind of split into 3 families. 1 are the halogenations, 2 are adding deactivating acids, and 3 are Friedel-Crafts, which are about adding carbons. So for these, each of these has a pretty idiosyncratic mechanism for making the electrophile. You do have to know these. That adds a wrinkle to studying the reactions. But again, I would think about it as every one of these reactions in this family. You not only need to know the reagents, but you need to know what is that great electrophile that those reagents make in situ. And so BR2 and FeBr3, the BR2 associates with the FeBr3, and this thing becomes a really great leaving group. So benzene can come in and do a bloop, kind of SN2 attack. Over here, for adding a nitro group and NO2, our really good electrophile is NO2+, where we attack this and push up. But this NO2+ we make from nitric acid and sulfuric acid. Similarly over here, to add an SO3H, our good electrophile is SO3H. And so it's how do we make that from SO3 and H2SO4. I'm not going to go beat for beat through those mechanisms, mostly just because that's kind of more of a just memorization question to work on. But what I do want to talk about is a little bit of Friedel-Crafts, which, again, I don't have this written, so, bear with me, and we'll see what happens. So, the core question for Friedel-Crafts is how do we add carbons to a ring? And we have two variants here. So if we have a benzene ring, one way that we can do is we can add carbons just fully directly. And if we add just carbons onto the group, maybe I'll do it with an ethyl. This is called a Friedel-Crafts alkylation. And the reagents that we use for it is we use an alkyl halide with AlCl3, this strong Lewis acid. The other way that we can add carbons onto a ring is we can add it with a carbonyl. And the reagents that we use for this are an acid chloride with AlCl3. So over here we have acid chloride and alkyl halide. Now, this word acylation, there's a kind of functional group hidden in here that we haven't explicitly named. But if you have like a carbonyl with an R group on it, we call this an acyl group. So like all of our CAD reactions typically are called acyl transfer reactions because we're just changing who has the carbonyl and the R group between like a carboxylic acid or a chlorine or whatever in CAD land. So these are kind of our two big options. And with this, one of the things that we need to think about is, okay, if we need a really good electrophile for Friedel-Crafts, what are really good carbon electrophiles? So let's start off first with Friedel-Crafts alkylation, or acylation, sorry. So, yeah.
Does this reaction work with any RCl or is it just...
We're going to talk about it. It's coming. So with Friedel-Crafts acylation, we are starting off with our acid chloride and our AlCl3. And the first step is your chlorine is going to associate with your AlCl3. Chlorine here has now two bonds, so it has a positive charge, AlCl3 has a negative charge. And now, what we're going to do is, because this thing is a really good leaving group, kind of like how we saw in like the Cl2 AlCl3, this is the part where normally a nucleophile would just do an SN2 attack if it was just a chlorine-chlorine. But here, when we have this carbonyl next to it, we are going to do this fun little funky move. Our fun little funky move is we are going to push down and kick this leaving group off. And when we do that, we make this CO triple bond that puts a positive charge on the oxygen, and this is called the acylium cation. She, to me, is a super carbonyl. And when I typeset this, I'm going to put a little Superman cape behind her. Because it's like this polarized carbonyl CO double bond, but we now have a positive charge on oxygen, making this even more electrophilic. And so at this point, our benzene ring, which I'm just going to write as nucleophile, can come in and like attack and push up. And then after our full EAS reaction, what we get is now that triple bond was turned into a double bond, and we still have our R group on it. So that's kind of the general setup for Friedel-Crafts acylation. This is our really great electrophile of the acylium cation. And Friedel-Crafts acylation is a really robust reaction. It has very few limitations. Our only limit is you can't use formal chloride, HCl, one carbon. You need 2+ carbons. And it's just because this thing will spontaneously collapse into HCl and CO, and so like it's just not going to react. There are ways you can force it to react in like pressure conditions and things, but that's kind of beyond our scope.
Wait, where did the benzene ring come from? Is that the R group?
No, it's the nucleophile here. Then our other option is Friedel-Crafts alkylation, and she's the slightly more complicated girl. For Friedel-Crafts alkylation, basically we have 3 ways of generating the electrophile. So starting off, way 1, we have an SN2-like reaction. So this would be, we have our alkyl halide. She's going to associate with AlCl3. And I'm going to make that into a curved arrow here to make that a little bit clearer. We now have the Cl, AlCl3 plus minus situation that we had before, where this is a really great leaving group. And we typically do this when our R group is methyl or primary alkyl halide. So now our really gray electrophile, and I'm going to put our gray electrophiles for all of these actually in purple, just to kind of make them consistent here. This is our really great electrophile if we're doing a SN2-like. So this is just a more activated alkyl halide. So at this point, a benzene nucleophile can come in and literally just do an SN2 style attack. So bloop, bloop. And again, I'm just using nu here for benzene because the thing that we care about is how we make the electrophile. Once we have our good electrophile, it's the same EAS reaction every time. And so just to kind of save some steps in time. And this will allow us to put our R group on the benzene. So again, this is for methyl or primary alkyl halides. The second way that we can do it is SN1-like. So that is, we have our RCl, we do the same exact thing with AlCl3, and now, plus minus here, this we typically do when our R group is secondary or tertiary. So when our R group is secondary or tertiary, at this point we have a great leaving group. And what's going to happen is the leaving group's just going to leave, SN1 style. So at this point, this makes our great electrophile, which is a carbocation. At this point, the nucleophile can come in and attack. And then we've added our R group on the ring. So kind of first type was activated halide with just associating with the AlCl3, SN2 attack. We could do a carbocation, SN1-like. And the third way that we can do it is through an alkene and acid. So this would use some sort of alkane like this. And maybe I'll put an R group on it. This can go and grab a hydrogen. And when we do that, it's going to make a carbocation. That's our good electrophile. So yet again, our good electrophile is a carbocation. We just have a different way of generating it from an alkene. And then the same thing here, our nucleophile benzene can go and attack. And then we get, at the end of the day, our carbons added over here. So, lots of different ways to do things with Friedel-Crafts alkylation. But the thing is, she has some issues. So, first issue is one of over-alkylation. So essentially, if we were to do like benzene here with methylchlorine AlCl3, we are going to get the product with 1 methyl added, but we're also going to get the product with 2 methyls added It can also be added like side by side. They can be added like ortho to each other. And we're going to get the product with 3 methyls added. You can even get the product with 4 methyls added. Don't worry about writing all of these combinations, but just seeing, okay, we can add a lot. And the reason is because the alkyl group is activating, which we'll talk about in a little bit. So issue number B is when we are doing this through a carbocation, they can rearrange. So, like let's say you're doing benzene and you are reacting with this boy. What you are going to get is not going to be this verbatim product here. You are not going to get this. This is the product where we are just literally plugging in the benzene where the chlorine was. Instead, what's going to happen is when we make our carbocation, our carbocation is going to have a little rearrangement that can happen. That is going to make it so our reactive carbocation with the benzene looks like this. So the product that we are going to get instead is actually this girl where we have 2 methyls attached at the carbon site, and then we have this ethyl on it. So this has a rearrangement.
Where does that bond go in the rearrangement?
The hydrogen bond?
Or the chlorine just like
Oh yeah, so this associates with the AlCl3, and then she leaves and makes the carbocation. Like this bond, the electrons go with the chlorine.
like there, where did the, in the rearrangement, where did the bond go?
This bond with hydrogen, it's right here. I just didn't draw it.
Oh, okay.
So no, you're all good. Okay, so these are kind of a couple of issues with alkylation, but I'm going to introduce one more issue that Logan didn't talk about, and I'm just going to briefly say it, not doing a ton of it. Basically, it's this idea that most primary alkyl halides can't be used, can't effectively be used. So what happens is, let's say we try to do this Friedel-Crafts alkylation with propylchlorine. So here, if we try to do this with propylchlorine, the product that you would expect is this. And you do get this, but you also get some of this product here, where you get an isopropyl added instead. So this comes from a weird rearrangement. You are not responsible for this mechanism, but I think it is interesting. So after you make this activated boy, what can happen is you can do a rearrangement at the same time as this gets kicked off, and it becomes a carbocation. This thing that looks primary, it should do SN2. It can sometimes do this weird rearrangement that's kind of SN1 style. And so, largely alkylation, you're going to want to try to avoid when you can, because you can't add long straight chains, you have carbocation rearrangement, and you can do over-alkylation. So we need a solution. And the solution that we can do, and it's the last thing here, is we can do an acylation with a reduction. So the key idea is you add your carbons via acylation, and then you remove the carbonyl. So for example, if we were to try to make this product over here, the non-rearrangement propyl, what we would do is step 1, we would do our propylchlorine with AlCl3. We're doing our acylation, and we've added our 3 carbons. And then the way that we are going to do this to get all the way to the alkane is a 3-step little mini synthesis route. 1, how do we reduce a carbonyl to an alcohol? Yeah, soft boy. Then we are at our alcohol level, so we go very briefly to alcohol. How can we turn an alcohol to an alkene? And why are we doing an alkane? Well, we're trying to make it into an alkane, right? You only know one reaction that makes alkanes, and that's H2 added to an alkene, right? So we need to make an alkene. How can we turn an alcohol into an alkene? Is alcohol a good leaving group? No. Yeah, so there are a few routes. You can make it a good leaving group and then do an E2 elimination, but there's a way that we can do it in one step. Conc it. Use conc H2SO4. That is going to make it into an alkene here. And last step, H2, palladium on carbon. So it gets around that limitation of the rearrangement, the overalkylation, all these things. It's really useful. And in most other like 2-semester OChem classes, this exact transformation, they teach one-step reactions that do this. And there's some of my favorite reactions in OChem too. I call that family of reactions Women Are Powerful. Just because they are like really, really fierce transformations. And they have names: Wolff-Kishner, Clemenson, Mozingo. Like, what's going on? And they just have like fierce reagents as well. But this is the way that uses only reactions that y'all have seen before. Yeah? Yes. That's from lecture 6. That's the way that we can guarantee E1 elimination. Cool. So I know that this was slower because we were writing out things, so thank you for bearing with me as we were going over it. But again, I just wanted to kind of lay out the Friedel-Crafts a little bit more because that's, I think, the hardest one of these and the ones where there's the most thinking and variation in here. So that's the thing to be aware of if you're trying to add carbons on a ring and one of these problems comes up, then you're going to need to use this acylation and reduction strategy. Any other questions on Friedel-Crafts? I'm actually doing right on time. That's crazy. For 9 a.m.? On time? Wow, couldn't be me. So let's talk about some of the theory involved with these reactions, because the hard part isn't really the reactions itself, it's everything around the reactions. So first off, we need to get this relative nomenclature. Yeah, my place memory of when I first learned these reactions when I was in OChem 2, it was 10 years ago, crazy. It was spring of 2016. I was a senior in high school. I went to the local coffee shop, Jittery Joe's, and it was right after Beyonce's Lemonade came out. And so I set up camp. I was in that coffee shop for 12 hours, and I was listening to Lemonade on a loop, and then just drilling EAS reactions, doing all of this. So I can't think about these reactions without thinking about Beyonce's Lemonade on repeat. But specifically I say that because whenever we have something on the ring, R, we call it our R group on the ring, the positions next to it are ortho, O, and then the one away from that is meta, and then the opposite is para. The way I remember it is romp. I imagine benzene wearing a little romper and feeling really cute and listening to Beyonce. So that's my little mnemonic, ortho, meta, para. So this totally depends on where your R group is. If your R group's up here, ortho's there, or there. If your R group's over here, your ortho positions are now there. It's all a relative nomenclature system. So what's the relationship between X and Y? Ortho, meta, or para? Yeah, what about X and Z? Meta. What about W and Y? Para. What about W and Z? Meta, great. So now, if you had a benzene ring with a carboxylic acid, we do a little portmanteau. It's benzoic acid, right? Benzene carboxylic acid, fair enough. If you add an OO bond here, this is like peroxide, so we do another portmanteau, peroxy benzoic acid. And then if you add a chlorine meta to it, it's metachloro peroxy benzoic acid MCPBA. An icon. You didn't even know how to understand her before. Her one-step fierce, what does she make from an alkene? She turns an alkene into an epoxide. She's fierce. Know about her. I like her. And now you can understand her name. So, when we have substituted benzenes versus just reacting with plain Jane benzene, there are basically two questions that we are asking about how does the thing on the ring affect the benzene. So the first question is a question of activation. Does the thing that we put on the benzene, does it make the benzene more reactive in EAS reactions or less reactive in EAS reactions? And typically, this is based on whether or not the thing that's on the ring is an electron donating group or withdrawing group. If it's donating electrons into the ring, let's think about, for the EAS reactions, is benzene a nucleophile or an electrophile? Say it. It's a nucleophile, right? It's the one doing the attacking. So if you have an electron donating group that pushes more electrons into the ring, is it going to be a better or worse nucleophile? Better. It has more electrons to go and attack stuff. Okay, so electron donating groups make it a better nucleophile, and withdrawing groups make it a worse nucleophile. So that's one question, activation. The other question is direction. Now that there is one thing on the ring, where will the next thing be added? Will it be added ortho, meta, or para? And directing effects, that's what we call this, like where is the next thing added? It's determined by resonance. So we have two general rules here. So our first key fact here is electron donating groups are activating, what we said earlier, makes it a better nucleophile, and they direct ortho-para. So if we have an electron donating group like this NH2, this can donate via resonance, right? It can push electrons literally into the ring. And if we look at the resonance structures, we're basically hopping around a negative charge. And so what we get is there are 3 carbons here that are kind of electron hotspots. So if this was to go and be a nucleophile, we would most likely add our electrophile at these positions. And these positions happen to be ortho and para relative to our R group. So we say electron donating groups are ortho-para directors. This resonance, you should get comfortable with writing several times, just because you want to be comfortable with this and pushing electrons around a whole benzene. Yes. The other thing is alkanes are also electron donating, but how are they electron donating? Via what? Say again? Hyperconjugation. So this is like how they stabilize a carbocation, how they donate a little bit of electron density. So alkanes are donating via hyperconjugation. Now, again, we said that this directs ortho and para. So we're going to get a split. Like if we have this methyl and then we're trying to nitrate it here, we can add our nitro group ortho or para. And generally speaking, when our R group here is pretty small, we favor ortho simply because there are 2 of them. And so it's kind of like 2/3 ortho, 1/3 para, when our R group is really small. However, if we have a bulky R group, we tend to favor para. R class, we rarely test this. Some classes are really like intense about it. For our purposes, you can put it where you want it. If it's an ortho para director, you can make it ortho or you can make it para, and we're like, sure, that's fine. Second key fact, electron withdrawing groups are deactivating and direct meta. So electron withdrawing group, here we have a like carbonyl outside, and we can do a resonance and pull electrons out of the ring. We're pulling electrons out of the it makes it a worse nucleophile. But then also, now the thing that we're passing around at these ortho and para positions are a positive charge. So I know that this is kind of weird logic, but if these are really electron deficient, then that means the meta positions relatively have more electron density around it. They are the only carbons that don't have a positive charge in resonance when you're tossing it around. And so that's why if this benzene ring is going to go and attack something, it's going to add meta. It's going to direct the next thing to be meta. Now, we can also have something without resonance withdraw. So if we have like an atom with a positive formal charge, how is this withdrawing? Via what? What are ways that we can withdraw electrons? Resonance and one other. Induction, yes. Remember, a positive formal charge functions like being really electronegative. It's going to pull electron density away. The other key fact that you need to know, and it's an important one, is sometimes some groups can be so deactivating that they shut down certain reactions. So if you have a nitro group or a sulfonic acid on your benzene ring, you cannot do Friedel-Crafts. Friedel-Crafts alkylation and acylation fully will not happen if you have a nitro group and a sulfonic acid group. You can do things like bromination and chlorination. You can add more nitro groups. You just can't do Friedel-Crafts. Friedel-Crafts is a little picky. So, with this in mind, I have made you a gaussified chart. And the gaussified chart here, our standard of comparison is just a hydrogen, like benzene. And if we have something with like lone pairs or resonance here, it's going to be activating and ortho-pair directing. If we have alkyl groups, these are going to be weakly activating via hyperconjugation and still ortho-pair directing. And then over here, if we can withdraw via resonance or if we withdraw via like a positive formal charge here, these are deactivating. They make it less likely to do more reactions on the ring, and these are meta-directors. There's one weird row here with the halogens. So halogens are the weird one thing that doesn't work with these two rules, and it's because it has competing forces here. If we have something like fluorine, fluorine's super electronegative, so it's withdrawing via induction, but it does have a lone pair, and so it can donate in via resonance. Is this a good resonance structure? Positive charge on fluorine, the most electronegative element? Nah. So this is not a good resonance structure. So which of these effects do you think is most important overall? Induction or resonance? Induction, that's weird. Normally we say resonance is much more important, right? But here it's because this resonance structure puts a positive charge on fluorine, it's really unstable. So this is really weak resonance. So because induction is the most important, we say halogens deactivate the ring. They make the ring less reactive. It's pulling more electrons out than it's donating. However, all of our directing effects, all of them are determined by resonance. And so because it is electron donating via resonance, it is still an ortho-para director, following this rule. So again, these are the only kind of exception to our rule of donating groups are activating an OP, withdrawing groups are meta-directing and with deactivating. And so I have a sound cue. To them I say, fluorine. Fluorine, you are the only exception. Fluorine, you are the only exception. My bro, bromine, you are the only exception. And finally, Miss Iodine, you are the only exception. They're just enough in the chorus for all of them. So we have that. It's the only exception to our rules over here. Okay, last thing I want to do here is talk through this quick example of if we are having to add a bunch of things onto a benzene, the hard part's not figuring out what the reactions are. when you study your reaction basics, you're going to be like, okay, I do Friedel-Crafts acylation, I do nitration, I do bromine, and you'll have the reagents memorized. The hard part is figuring out the order. So I laid out every possible path, and we're going to think through it. So first off, let's imagine we added our bromine first. Is our bromine meta-directing or ortho-para-directing? Ortho-para, only exception. Great. So now let's imagine we add our nitro group after it. Is this correct? It added ortho, and then here, if we did Friedel-Crafts, it would add para. So those are both fine, okay. But then if we try to do Friedel-Crafts after our nitro group is added, does that work? No, this pathway does not work because shutdown of Friedel-Crafts happens after our nitro group. Well, now we have two things on our ring if we want to try to do this route and do our nitration last. How is our bromine directing? It's ortho-para to it. And then what about our carbonyl? How does it direct? It's withdrawing, so it directs meta to it. So the meta positions to it line up exactly. So that works. Both of our directing effects agree. So this synthesis route is valid. All of our directing effects work. We're not doing Friedel-Crafts after a nitration. So like this, if we do start off with our nitration, we know that this is not going to work because we cannot do our Friedel-Crafts after a nitration. So we're not going to do Friedel-Crafts first. And then over here, imagine we did our Friedel-Crafts first. Friedel-Crafts, we said that this carbonyl is meta-directing, right? Is this meta, the bromine here? Because that's where we want it to be to get this product. Is this meta placement? No. So this one doesn't work because it's a meta-director. This one's meta, sure. But now, if we did our carbonyl, it's a meta-director. So it's going to direct here and only there because the other meta position is taken. And then our nitro group is another meta-director. So it's going to direct here. But we want our bromine to add here. So our directing effects won't work for this route. So you can see of all the possible combinations, only one of them actually worked with our directing effects. Yeah?
On that bottom one, is it also deactivated anyways?
It is, but you can do a bromination after it's deactivated. You just can't do Friedel-Crafts after it's deactivated. That's the important part. Now, on the practice page, we're probably not going to do these practice syntheses because I want to talk about the synthesis question and I want to talk about how to study reactions. But I have some info boxes here. So one of them is, what do you do when you have multiple directing effects? Like who wins? And so I've kind of talked through that. And generally the rule is the most strongly activating one wins. Then there's also a little side note box here for aromaticity. That what happens if you have a pi bond that's outside of the ring? What do you do with that? And so I'll let you all read through this. This will be relevant for homework. So I would come back to these. But that's basically all I have for directing effects here. Questions before we go on to our last chunk? Welcome back to How to Study Reactions, Part 3. Wow, you made it. Part 1 is what are reactions? What do you look at? Part 2 was, okay, I need to shove these inside of me, and I need a time-effective way to get the reaction basics down of just how do I write the mechanism, how do I predict the product? Part 3 is really about exam 2. So let's talk about exam 2. The challenge for exam 1 was you had a bunch of different skills and also baby's first reactions, what are reactions, doing your first little baby synthesis. Now the challenge is you have 80 plus reactions. So there is this big volume game. This is historically what the exam 2 outline has been, and I think that we're going to keep it. It's exactly what the practice exam outlines are. You're going to have 3 pages of line reactions, box problems. one of those pages is going to be a substitution elimination page. You're going to have 2 pages of synthesis, 2 pages of mechanism, and 2 pages of theory. Theory questions include things like, what is the fastest SN1? What is the fastest SN2? What's the most reactive CAD? Then we have things that are lecture 9 of aromaticity. We have directing effects. We have, are the things on our benzene ring activating? Yeah, I think that's most of them. We could also do like carbocation stability / radicals. That's what I mean by theory. These pages should be your easier points. These are going to be like fill in the bubble type questions. But 7 of your 9 pages are now reactions. That's a lot. And of those, 5 out of 9 questions are line reactions or synthesis, are working at that line reaction level. So right now, I would say your number 1 goal is to get through problem set 5 as quickly as possible. I would say try to have it done maybe by like Saturday. Today, finish up the skill builders. Tomorrow, try attempt at the challenge problems, get like 90% of it done. Go to help room on Monday, ask some questions, and then submit it. But you really want to switch over to studying and starting to put all this together as soon as you can. So maybe Sunday or Monday. And then Sunday and Monday, the first thing that you should be doing in your studying is getting all those reaction basics down of, can I generate the fake mechanism for the product, and can I draw the mechanism for the mechanism questions? Those are active recall die-drill things. We've talked about a lot of this in our meetings. But now the question is, okay, maybe you have these reactions down, but how do we organize them? How do we kind of put everything together? So there are kind of 2 big issues that I see that your studying has to do after you have the very basics down. The basics is like you bought the tools from the store and they're in a pile in your garage. So the first one is a tractability issue. If you had to memorize like an 85 list long of reactions as a just standard list, like that's just going to be overwhelming. It's not going to make any kind of like organization. Again, you're like sorting through all of the reactions to try to figure out one to use. It's not going to work. So something in your studying needs to organize all of these reactions and condense and compartmentalize them. And so the strategy that I prefer for this is to think of them as reaction families. These are all the reaction families for the entire course. There are like 14. And I like to think of them as they are your toolbox drawers, I guess. And not only is it helpful to have these drawers, you need to go to the container store. You need to subdivide these drawers. Redox line reactions, you have your oxidations and reductions. Within your oxidations, you have the ones with pyridine as the sidekick, and you have the ones with H2O as the sidekick. Within the reductions, you have the ones that make amines, and you have the ones that reduce like a carboxylic acid. Within the CAD family, you have the simple CAD reactions where all the mechanisms are the same, and then you have the weird ones, which are the Sockle and the nitrile hydrolysis. You need to make some sort of organization system so that it becomes your workroom where you can build the birdhouse and all the tools are on the wall or in the drawer and you know exactly where they are. So I think that something that you should do should engage with that. The warning I will give is if you are making a review sheet, do not make it pretty. Do not spend hours upon it. You really want it to be fast and dirty, something to just have it organized in your head. The second big issue is integration. So right now, y'all are kind of like, oh, I'm in lecture 6 mode, substitution elimination. Oh, I'm in lecture 9 mode, benzenes. But we need to do things that are going to have you bounce around between lectures 3, then 8, then 9, then 2, then 5, then whatever. Not really 2. 2 is like MOs. They're everywhere. So I'm going to talk about 3 strategies to work on this. So the first one is to do a nature walk, a chemical nature walk. What we're going to do is we are going to start with a small molecule, and I'm literally just going to be like, what can I turn this into? Okay. Well, I have an alcohol. I'm gonna turn it into a bromine. What reagents do I need? PBr3, great. And now that I have a halide, I have a good leaving group, so maybe I'll replace it with like a nitrile. What reagent should I use? ACN. Yeah, and as I'm doing this, I'm thinking alkyl halide, Nitrile, I'm thinking about functional groups. Okay, nitrile. What reactions could I do with nitrile? Well, I could turn it into a carboxylic acid. Yeah, that was a weird cat reaction. Okay, what reagent do I need for that? H3O plus, yeah. Okay, now I'm in CAD land. I'm in Grand Central. I can go anywhere I want in CAD land. So what if I did DCC with NH3? Well, that could make an amide, right? NH2. But then I'm I'm tired of amides. You know, I want to leave the Emerald City. How could I go back to a carboxylic acid if I wanted to return? How can I go from an amide to a carboxylic acid? Say again? H3O plus, great. Okay, so I'm back in CAD land. Where do I want to go next? I want to leave CAD land. I've had it here. How do I go and make it into just an alcohol? I'm doing a reduction, so I'm using lithium aluminum hydride, Et2O, H+. I know that this feels frivolous a little bit, but part of it is right now, y'all are in a fear state with reactions, and we want you to be in a more creative flow state with reactions. And doing something like this, I think a little bit takes the piss out of it. You know, it's I can just build things. You know, I can just. It's the difference of doing art for a class and then doing it for pleasure. It just gets you thinking and brainstorming about the ways that you can turn molecules into other things. So I like a nature walk as especially a warm up. If you're starting off a study session, okay, let me do a little nature walk, see where I go. Second strategy. Do y'all have friends? Particularly friends in this class would be helpful. So what I think you should do is I think that you should find each other, message each other today and be hey, we're going to do a synthesis potluck on Monday. Cook up your best synthesis. And everyone in your little friend group writes 1 or 2 synthesis problems. You will write a answer key version and a blank version. And then you'll come together at the potluck and you'll all swap synthesis. And then suddenly you have 6 more synthesis problems to do that are targeted for our class. More than that, I know that there are synthesis problems now that we're releasing 4 exams that are more available. The process of writing a synthesis question actually will be so helpful because you are putting yourself in my shoes when I am writing your exam of okay, how can we use all these reactions? Oh, am I really making a synthesis that's only really using lectures 3 and 5? How can I sprinkle in lecture 8? How can I kind of make a balanced synthesis problem? 1. 2, be mean to your friends. Try to write a synthesis problem that's going to stump them. Try to write a hard synthesis problem because you're going to have to be thinking through that. And that's going to prepare you for me writing hard synthesis problems for y'all. You know? I think it is a really gold tier strategy for how to do synthesis and to make you, again, in this different position to reactions where you're feeling in a little bit more creative space. Last strategy, reaction webs. So for any functional group that you want to work on, list the functional group in the middle. And what you're going to do is you are going to try to list all the different ways that we can make that functional group and all the different things that we can turn it into. So the other thing with this, label your functional group names as well. I know it seems redundant and you're I know what a carboxylic acid looks like, but you're really training yourself to brainstorm. This is the thing that's going to be most helpful for synthesis of oh, okay, if I have this, what are all the things I can turn it into? Or if I have it in the product, how can I make it? So can someone give me one way to make an alcohol?
Carboxylic acid.
Yeah, we can do what with carboxylic acid? Yeah, we can do lithium aluminum hydride. I'm not going to write out the full one for time. We can also do that with an aldehyde, right? How else can we make an alcohol?
The calcium version?
Calcium?
Not calcium, the palladium. Can you do palladium?
The NAD+. Oh,
That's biology. Palladium is reducing an alkene?
Sorry, CuCl3.
That adds carbons 1,4 to an enone. Wait, what?
I forget, but it was to do 1,2 addition only for alcohols.
But we don't have an enone.
NaO.
Oso, do you have one? You seem maybe. How about from an alkene? H3O plus, high separation. Okay, we have an alcohol. What are things that we can do with the alcohol? Could I make it into leaving groups? Okay. Could I make it into an acetal? What else could I do? The first time that you do this, you're going to be flipping through notes. You're going to be flipping through section notes and setting it up and thinking through it. But like, what are other things that we can do? Yeah, we can conk it. What else? We can make it from aldehyde and carboxylic acid. Can't we also turn it in an aldehyde and a carboxylic acid? What do we use for these? Chromium. And then if we're going to stop at the aldehyde, what sidekick do we need? Pyridine. And then if we're going to carboxylic acid, water. Can you think of one more reaction that uses an alcohol? Say one more time. No, because alcohol's not a good leaving group. So we could do that from here. Again, I'm kind of asking you a trick question, but do you see how this is good? You're scanning through all of the lectures and trying to draw connections and put them together. The one I'm thinking of is tricky. What if I combine it with a carboxylic acid and acid? What's that going to make? An carboxylic acid, an alcohol, and acid. It's going to make an ester. Sneaky, sneaky. But do you see how that can happen? Like, again, y'all are used to seeing the carboxylic acid in the center and then putting the alcohol in the arrow, but we don't have to. Same like the acetal. We can always switch them. There are 3 ways that we can make an alkene. One of them is E1, so we could do a conc H2SO4 situation here with an alcohol. One of them is E2, which is like NaET, and we have a halide. What's the other way we can make an alkene? From last lecture? From lecture 8, I mean. It was the reaction that mogs all the other reactions. Boxy boy. Vidig. So we can do this from some sort of carbonyl. So maybe I'll make it like this carbonyl, and then H2C PPH3 minus plus. Last one here, and I'm not going to do all of it. What are all the different ways that we can make a primary amine? There are only 2 ways in the entire class that we learn to make a primary amine. The dead stares on people's eyes right now. They're like, I don't like this. Yeah. Yeah, we can do an amide. And we can reduce it with lithium aluminum hydride. And what's the other one? It's right by that one. It's right next to it. Yeah, you both had it. So you can reduce a nitrile. So here, notice that this only has 2 carbons, and there's 1 carbon already in our nitrile. So this needs to look like this, like a methyl CN. And we can reduce that. You can do this with any functional group. You know, this is great practice. For these webs, I put them, and the annotated, you have a web like it filled out for all the ones I could think of. But make it with ethers, alkyl halides, carboxylic acids, amines, vicinodiols, epoxides, keep going. And then once you've made it, then it's going to take a while to make all the ins and outs. Once you've made it, erase everything but the arrows, set a timer. How quickly can you brainstorm and think of all the things that you can do with it? Use this to get the reagents memorized really well. Reaction webs, dihedrals and reaction webs are the 2 highest yield studying things that you can do for reactions. If you are not making reaction webs or doing some sort of active recall that's like a dihedral, it's not going to go as well. But you now know how to study reactions. Okay, so we started 5 minutes late, and I'd really like to do the synthesis. And so I'm going to go probably 5 minutes over from the end time. If you need to head out, you totally can, and you can watch the synthesis in 11, which hopefully my timing will be faster, but who knows. But this is the hardest synthesis I think you've ever seen, and I think it would be good to do together. So let's talk about it. All I want you to do is I want you to take 90 seconds, do your functional group analysis, maybe try to map some carbons, get some initial thoughts. I do not expect you to have like big sweeping information from this. I want you to read the room. One other question I want you to think about when you're doing this is how many carbons do you have in your starting materials? How many carbons do you have in the products? Okay, so initially we have an alkene and we have a ring, right? Four-membered ring. And we only have 6 carbons. But in our products, we've made 2 primary amines. We now have 8 carbons, so we've added 2 carbons somehow. And primary amines, hey, we just did our brainstorm of that. There are only 2 ways in this entire course that we can make primary amines. So that means if we're thinking backwards, we had to have either come from this structure or this structure with amides or nitriles. So, with me so far, / is this something close to what you were noticing of like, in terms of functional groups, and then maybe connecting that to the fact that we only can make amines through some of these reactions? You might not have written out the structure there, but. So with this, let's list out the challenges and the issues of this. So challenge number 1 is we need to add 2 carbons. Making carbon-carbon bonds, we said, is a fundamental challenge of organic chemistry of this class. What are ways that we can make carbon-carbon bonds? Grignards, yeah. What else that's not organometallics? Ways of making carbon-carbon bonds. Yeah, Frito Crafts, great. What else? I'm looking for 2 more. It mogs all the other reactions. So fancy. Davidic. That adds carbons via the ylid, yeah. And then what about just SN2 with NaCN? That's another way that we can make a carbon-carbon bond, carbon nucleophile. That's about it. Until lecture 10, these are basically the only ways that you know how to make carbon-carbon bonds for the exam. So if you need to add carbons, you've done one of these. Okay, so second issue. We need to open a ring. Does anyone have an immediate association with a reaction that's going to open a ring? Radicals can, but do we like doing radicals in a synthesis problem? No, because crazy things can happen. That just makes an alkene. Yeah. Yeah, you're totally... Okay, can I say a mnemonic that's a little inappropriate? I didn't know it was inappropriate when I came up with it. So the reaction from alkenes that you should immediately associate with for busting open a ring is ozonolysis. And I used to call this reaction Lord Split Me Open, which I thought was a sincere religious term. I thought it was like, wow, finding the Lord's guidance in your life. I was like, oh, people make inappropriate jokes with that online. But I have since learned that that's not a religious phrase at all. And so I am a little embarrassed by it. But also, that's how I remember ozonolysis breaking open rings. It's Lord Split Me Open, you know? So ozonolysis, if we have an alkene in a ring, this can chop that alkene and make 2 carbonyls. Wow, that really got Federico, okay. Last issue over here is we need to add the nitrogens. So again, we can do this either via nitrile or we can do this via an amide. Okay, so just based on laying out these issues, are there any routes here that you think would be kind of simpatico, that we can accomplish 2 of our things at once? Specifically, like which of these carbon strategies?
S-17, NaCN.
Yeah, if we add our 2 carbons via 2 CNs, that can get us somewhere over here, right? Okay, so let's kind of like try to work backwards even. So if we have NaCN and we're trying to go to our final product here, so let's kind of X that out. Then the thing that we want is 1 lithium aluminum hydride with Et2O and 2 an H plus workup. But then if we're trying to do SN2s to install our nitriles, then the thing that we want in that place is a leaving group. So I'm just going to put a bromine. So then we can add NaCN. With me so far? So now our target is how do we get to this? Well, we need to split open the ring. Ooh, our alkene, if we just tried to do ozonolysis right now, that would just chop off a carbon, right? So that's not going to split open the ring. So we need to like shimmy over and put an alkene in this ring somehow. We can make alkenes via eliminations, right? So, okay, if we need to make an alkene, alkenes are made from alkyl halides with like an E2. So let me just try, why don't I add a halide to an alkene? What reaction could add a halide to an alkene? PBr3 takes an alcohol to a halide, but if I'm just wanting to add a, that adds 2 halides. HBr. No, you're so close. HBr. And so it's really tempting to write this, but HBr proceeds through what kind of mechanism? Do we form a cyclic intermediate with a bromonium, or do we do a carbocation? Carbocation. And anytime we are doing a carbocation, what do we have to do? We have to check for rearrangements. So we add our H, we have a carbocation. Is this going to rearrange? Hell yeah. We have a carbocation next to a strained ring. It's going to open up. We now have a 5-membered ring here in a carbocation. Is this going to rearrange further? Hell yeah. It's going to do a hydride shift. So now we have a 5-membered ring with our carbocation here. And so our actual product where we add our bromine is going to look like this. So we've expanded our ring. We haven't split it open. But in order to split it open, we need an alkene, right? So what reagent can take an alkyl halide into an alkene? We're doing what type of reaction here? E2, right? So what do we need for E2? What's our most important thing? Base. Give me a base. Let's use, instead of NaOH, I'm going to use my favorite, Naomi. Naomi. Could I use Kotbu?
Yeah.
We couldn't use Kotbu here because it would make a terminal alkene, right? So we have to use a smaller base, so Naomi or NaOH. Oh, shoot. Sorry. My bad. My bad.
Would NaOH work or not?
Yeah, that would work. Okay, so now we have an alkene. Ready to bust it open? So let's do ozonolysis. And I'm just going to use DMS for the second step. I'm going to do the reductive conditions. You can probably do it both ways. So when I do that, my fake mechanism is I just put carbonyls on both sides. And now to make this a little bit easier, I'm just going to try to redraw this like the product. So I see 1, 2, 3, 4, 5, 6 carbons over here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I'm just going to redraw this like the product. So over here I have my aldehyde on the end, here I have my ketone. Okay, so now I'm at a ketone aldehyde state, and I need to get to alkyl halides. Okay, what could I easily turn a ketone aldehyde into? What are some brainstorms? Right now we're at the wrong oxidation level, right? So how can I go down in oxidation level? Reduction. Let's try NaBH4 MeOH. Oh, I think I added a carbon accidentally. 1, 2, 3, 4, 5, 6. I did add a carbon. Sorry about that. Okay. So now OH is here. I have an OH here. We're so close, aren't we? Yeah.
I just have a quick question. In terms of reduction, does it matter if you use lithium?
No, that's just more steps.
Okay.
Yeah. If you had other functional groups present, you might want to think about, oh, is lithium hydride going to affect that? But yeah, here you could use either. Yeah. Okay. Can we turn an OH into a Br? Say it loud.
PBR3.
We can use PBr3. This is making alcohols leave. And something like that, we've met in the middle. We're done. So recap, this was a lecture 8 reaction, followed by a lecture 6 reaction, followed by a lecture 8 reaction, followed by a lecture 3 reaction, followed by a lecture 7 reaction, followed by a lecture 6 reaction, followed by a lecture 5 reaction. This was a 1, 2, 3, 4, 5, 6, 7, 8, 9. 9-step synthesis. Challenging. Very challenging. But do you see how, like, our analysis, setting up the problem is half the battle? From there, we got the hint that, okay, let's try this SN2 with nitriles. We worked backwards. If we were only trying to work forward, honestly, I think it would be nearly impossible to try, like, figure it all out. It would take forever. We worked backwards. Then we thought about, oh, okay, based on our issues, we have to open a ring. We need to get an alkene on a ring. How do we shift over functional groups to get an alkene in this ring? Like, a lot of it was kind of working through these ideas of having a target functional group and then having our other reactions and our other functional group transformations on hand. This is where those reaction webs are going to be really, really helpful. But I went way over. I'm so sorry. I hope you have a great weekend. Take care of yourself. Get rest. Study. And I'll be seeing you on Monday for Help Room